Good morning, everybody. This is Dr. A, and I'm bringing you a little series on analytic techniques, and we are going to start with the spectrophotometry. So photometry measures light intensity without consideration of wavelength, just light, no light, or how bright it is, and how much of it might be absorbed through a cloudy specimen, like that. Spectrophotometry, however, measures light intensity of a specific narrow range of wavelength. So spectrophotometric instruments will measure the light that is transmitted by a solution as a specific wavelength of light is shone through it to determine the concentration of the solution. Chromogens are required in a chemical reaction to detect the analyte. So you have to have a colored chemical reaction, and then the intensity of the color is going to be proportional to the concentration in the sample. So here on the side of the slide, I have light as it's broken down into its various wavelengths, and then that determines different color spectrums in light. So in the 400 nanometer range, you're going to have the purple end of light. In the 500, it's going to be blue-green. 600 nanometers is in the yellow-orange range, and 700 nanometer is going to be in the red range. So let's look at practical aspects of light. So the color of something is determined by the wavelength that it reflects. Okay, so if it's red, it reflects red and absorbs all the other wavelengths. Okay, it will very easily absorb the color that is its opposite in the color wheel. So I have the color wheel here for you. So for example, if the chemical reaction in a cuvette is yellow, then it will absorb the blue end of the spectrum the most right here. So if it's yellow, it will absorb blue the most. If you shine yellow on a cuvette that has a yellow reaction in it, it's going to reflect that light, it's going to bounce and it won't absorb, and therefore you can't use that to detect the or determine the concentration of that sample. So if it is, if the sample is in this red-orange, it's going to absorb this blue-green the best. If it's purple, it will absorb green the best, etc. So whatever it is, it's opposite. And then Beer's law states that the concentration of a substance is directly proportional to the amount of light that is absorbed by that substance, or inversely proportional to the logarithm of the transmitted light. And so we can shine the light through a cuvette that is full of the chemical reaction with the analyte, etc. is being detected. So there's a color change that's going on here. Shine light through it. The more light is absorbed, and therefore the less is transmitted, the more concentrated the sample is. So it is a direct relationship. So the higher the absorbance, the higher the concentration. So we go small absorbance, small concentration, high absorbance, high concentration. As long as that relationship is linear or straight or predictable, so you can predict a concentration from the absorbance reading that you get, then the test is said to be linear in that range, and you are in the analytical measurement range for that test. As soon as the relationship starts deviating, and either negatively or positively, you've lost linearity, and that relationship is no longer predictable by this line that can be calculated. So this line here, where the ideal relationship is, that line can be calculated with the slope and intercept. It's a y equals mx plus b calculation here. And so the absorbance can be read by the spectrophotometer. So Beer's law says that A, the absorbance, equals the absorptivity coefficient times the path length times the concentration. The absorptivity coefficient is going to be determined by the manufacturer for the specific test. The path length is also going to be determined by the manufacturer, but it's going to be the size of the cuvette, how much the light how thick the cuvette is, or how wide the cuvette is, therefore the path of the light through the solution. And then C is a concentration, and that's what we're trying to determine. And so in here, C is going to be your unknown, and then the computer is going to get the absorbance reading with the absorptivity and the path length, which are going to be set for that specific analyzer and that specific test or analyte. And then the concentration can be determined from that, calculated solving for X, or here solving for C. And then it does the calculations using the y equals mx plus b slope line, and gives you also then the concentration at the end, which is what we're interested in. So the components of a spectrophotometer, you have a light source that is going to shine light, that's going to go through a collimator or lens that's going to focus the light on a monochromator, which can be a prism or a grating. The monochromator is going to make mono, one, chromo, color, is going to help split the light into its color spectrum, and then a wavelength selector is going to allow the selection of just one color within the light, and then that color is going to be shine on the sample solution where there's a color reaction happening, and so much of that light is going to be absorbed by the solution, and the rest is going to be transmitted into a detector, which is often a photocell, and then that converts the detector is going to convert the reading down to a digital display or meter, which usually would display the absorbance or send the absorbance value to the computer. So the light source and monochromators, let's look at those. Lamps must give polychromatic light, so light that can be split into all colors of the spectrum. For visible regions of the electromagnetic spectrum, or visible regions of light, you want to use tungsten or tungsten halogen lamps. For the UV end of the electromagnetic spectrum, you want to use a deuterium lamp. For the UV and visible range, you can use xenon lamps. So that's a combo, UV and visible. And then you can also use laser as a light source. And then the monochromator helps select a specific wavelength. So a specific wavelength would be a specific color. Mono, one, chromo, color, one color. Monochromator helps you select one color. So you can use a filter, so that literally just filters the light and makes it red, blue, green, whatever. A prism uses refraction to split the light. So this is illustrated here. Light is shone through the prism, and then this prism breaks it up or splits it into all of the colors of the spectrum. And then a diffraction grating. This is represented here. So light is shone on the diffraction grating, which bounces it, and as it bounces it, it splits it into the spectrum. And then you can also use fiber optics. So the cuvettes or the sample cells, here is one illustrated. This is where the chemical reaction is going to happen and where it is detected. So light's going to be shone through this cuvette. The photodetector converts light into an electrical signal. The most commonly used is going to be the photomultiplier tubes, because it can amplify a signal so that it is better detected. So this is a photomultiplier tube. And then a little bit more on spectrophotometry performance. So you want to ensure that your wavelength is accurate. If it says, 550 nanometers is what's needed, we want to make sure that that's where you're at. And so you can calibrate analyzers to calibrate the wavelength accuracy. Then you want to make sure to verify the linearity of the test. So that is often first set by the manufacturers, so you should know, but then it needs to be verified by each lab, and then that's verifying that this relationship line, this function line, is linear or straight across the analytical measurement range. And if it starts deviating, then you may have to modify the analytical measurement range up or down a little bit from what the manufacturer set it. Stray light in the spectrophotometer should be less than 1%. And then the absorbance accuracy can be determined using NIST standards, which are a set of glass filters. The application of spectrophotometry is that it is an integral component of most large chemistry analyzers, and this is a technology that is used to make determinations of glucose, blood urea, nitrogen, creatinine, total protein, albumins, all of your enzymes. So there's a wide application and very commonly used in the clinical chemistry lab. So moving to atomic absorption spectrophotometry. So it measures the concentration of an analyte by detecting the absorption of electromagnetic radiation, that's light, by atoms rather than by molecules. It is sensitive and precise, but it is complex, time-consuming, and labor-intensive, and that is why you won't see these in your average clinical lab, but they will be often used in reference labs. It is routinely used to measure the concentration of trace metals that are not easily excited. The principle of AAS is the absorption of monochromatic EMR, or one color of light, by an element in its ground state with a net zero charge. So what happens is the sample goes through a flame. The metal will dissociate from the protein because metals are carried by proteins in serum. So we need to split the metal off of that protein. And then as it's split, it will go into its ground state. And when it goes to its ground state, there's a light absorption pattern that can be determined that is unique to that metal. The detector will pick up any unabsorbed monochromatic EMR light, so any color in the spectrum that was not absorbed by that atom or by that element, and the concentration of that atom is going to be directly proportional to the absorption of EMR that it does in the pattern. So here is an example of the continuous spectrum of electromagnetic radiation, or of light, right here, and this is an absorption spectrum. So you can see that this atom or this element absorbed these specific wavelengths of light, and I believe this is the correct one for sodium. And you can also get emission spectrum, but that would be an atomic emission spectrophotometer. And so the emission pattern will be the wavelength of light that that particular metal will emit. And so they're like opposite patterns, as you can see here. And so this one would be for sodium also. And it gives you some just illustration of what emission patterns look like for different metals. So this is mercury vapor. This is low pressure sodium spectrum right here, and then this is a high pressure sodium spectrum. So it kind of gives you an appreciation of what it is and what it does. So, all right, so that wraps up spectrophotometry, and there will be more analytical techniques to come. Thank you.